Dear students, in previous lecture, I have defined vector subspace of a vector space over the field F. To understand clearly, we have to solve some problems mathematically. The first question is, show that set W is equal to set containing A, B, 0, triplet, such that for all AB belongs to field is a subspace of the vector space over V3 space V3 over the field F. So V3 is written triplet ABC for all ABC belongs to field members, and W is set of triplet like AB0 for all AB belongs to F. Clearly, W is non-wide subset of the V3. So first condition to be subspace is fulfilled. Now we consider two members, U A1 B1 0 and V A2 B2 0 triplet, where A1 B1 A2 B2 belongs to field members. Lambda and xi are two scalars because elements of the field are said to be scalars. So using NS condition to be subspace, lambda u plus xi v, lambda u, put down value of u and v. After solution, by definition of scalar multiplication, finally we find lambda a1 plus xi a2, lambda b1 plus xi b2 0 belongs to F. This element belongs to F. How can we say? Since lambda a1 xi a2 are the scalars, so in scalars multiplication is closure. Multiplication is closure as well as plus operation is also closure. Hence we can say this element contained in W. So we can say that this set W is subspace of V3 by NS condition. Now we define very important interesting theorem. Show that intersection of two subspaces W1 and W2 of a vector space V over the field F is again a subspace of the vector space. Since 0 is contained W1 as well as W2, so 0 is contained in the intersection of W1 and W2. So first condition to be subspace is fulfilled, that non-wide subset. Now using NS condition, we consider two members. U and V belongs to intersection of W1 and W2. Intersection means the element contained in intersection means it should contain in the both. So U and V belongs to W1 as well as W2 also by definition of intersection. Since W1 is subspace of the vector space over the field F, it is given. So by NS condition, for all UV belongs to W1 and for all lambda and xi belongs to F, lambda u plus xi v contained in W1 by necessary condition. Similarly, U and V belongs to W2 and lambda and chi belongs to F. Lambda U plus chi V again contain W2. So lambda U plus chi V is contained in W1 as well as W2. Hence this element contained in the intersection. So by necessary and sufficient condition to be subspace of the vector space is fulfilled. Hence we can say intersection of two subspaces of a vector space is again a subspace. Now next very important theorem, the union of two subspaces W1 and W2 of a vector space Vf is a subspace of Vf if and only if either W1 is subset of W2 or W2 is subset of W1. So proof. Let first we consider W1 is subset of W2 or W2 is subset of W1. So we have to prove that union of two subspaces is again a subspace. Since W1 is subset of W2 or W2 is subset of W1, implies that union of W1 and W2 will be equal to either W1 or W2, which are the subspaces. Hence, union of two subspaces is again a subspace of the vector space. Conversely, let us suppose that union is subspace of the vector space. Then we have to show that W1 is subset of W2 or W2 is subset of W1. So let us consider W1 is not a subset of W2. It means there exists at least one element alpha 1 belongs to W1 which is not in W2 by definition of subset. Now let lambda 2 be any arbitrary element of W2. Now alpha 1 belongs to W1, alpha 2 belongs to W2 implies that alpha 1 belongs to union of W1 and W2 and alpha 2 is also belongs to union of W1 and W2 implies that W1 plus alpha 1 plus alpha 2 belongs to union of W1 and W2 by the closeness because union of two subspaces is subspace. So additive abelian group, so by closeness it is true, implies that alpha 1 plus alpha 2 either belongs to W1 or W2. But if alpha 1 plus alpha 2 belongs to W2, implies that alpha 2 belongs to W2 equal to alpha 1 plus alpha 2 minus alpha 2 belongs to W2 by closeness. So implies that alpha 1 belongs to W2, which is a contradiction that alpha 1 not contain does not contain in W2. If alpha 1 plus alpha 2 belong to W1, now alpha 1 plus alpha 2 belong to W1 and alpha 1 belongs to W1. So implies that alpha 1 plus alpha 2 minus alpha 1 belongs to W1 by inverse and addition axioms or closure axioms. This alpha belongs to W1. Since alpha 2 belongs to W2, implied and alpha 2 also belongs to W1. So W2 is subset of W1. Hence the theorems.